shop. A flow shop it describes a situation like in a factory when you're trying to produce a product, and to produce the product it has to go through a series of machines. So let me see if that's not this one. So I think I told you that a lot of this stuff is a lot of this stuff you don't need to know. Here's a flow chart right here. Here you've got jobs, which can be orders, or it might be something you have to do for some customer. And to get the job accomplished, it has to pass through a series of steps, which we call machines. So each job has to pass through each machine. Now each job has an arrival time when it comes into the system and a due time when it has to be finished by. And the point is, you want to schedule your jobs so that the jobs are late as little as possible. Now there are two measures of lateness. If it's late at all, that's bad. So that's a penalty. But then beyond that, there's the amount of time that it's late. So both of those come into the penalty. Right? If I'm on time, that's great. If I'm early and on time, there's no difference.
Okay.
But if I'm 1 day late, that's bad. And then 2 days late. 2 days late is not twice as bad as 1 day late. Because it's less than twice as bad. Because if you're late at all, that's bad.
But it's still worse.
It's still worse, yes.
Okay.
So there's a slope. If you wanted to see how bad the impact is, it's a increasing slope, but the line doesn't pass through the origin. It passes through the y-axis.
Yes.
All right, if you get the picture.
Mm-hmm.
All right. So that's the basic problem. You've got machine. You've got you've got jobs. You've got several machines, and you want to get them out so that they'll be late as little as possible.
Okay.
Right. Yeah. So this is job shop. So forget all this stuff. We're just doing flow shop. I think I told you what to focus on. That's so. All right. Now this is just saying that in some formulations of the problem, they pass the jobs through. Once you put the job into the system, it stays in that order. So if you decide to do job 1 first, then job 3 second, then job 2 third, and job 4 last, then you have to use the same order for every machine. So you just pass it through like that. No, but we're doing the non-permutation flow, which means you can vary the order. You could job 1 could be the first through the first machine, but you could lay it aside and do job 2 first on the second machine, if that's helpful. So does that make sense?
Not quite.
All right. Well, let's see if I can draw something. I should have this here somewhere. Scheduling. All right. I have a whole different notebook for that. Here. I guess this is it. Yeah, this is it. All right, let me get my tablet so I can. I guess what's going to help you most is me sharing the code with you. I guess I haven't done that yet.
I didn't know if I was going to be making something from scratch or not.
No, it's not from scratch.
Okay.
You can have something that's built that doesn't work well.
Okay.
and figure out why it doesn't work well and make it better. Right. So, so let me just do the first one just so that we have. So we have here. This is the days late. Just to, I think you know this, and this is the penalty. And then it's like this, right? Something like that. Right. So now,
Okay.
so here we have. So we can. Let's do this. Okay. So here I have jobs 1. So here are the jobs. J1, Jn. Oops, that's a G. I'm thinking French here. Okay, through Jn. And machines, I'll call them C1 through Cn. Okay, so what this means, so a schedule will be some specification. If you want to specify the order of the jobs, J, on each machine. So here, I think I don't remember exactly how I do this, but all right, so these are machines, and then these are jobs. Right? So there's J1 through Jn, and this is M1 through Mn. All right, now, what's the first job into machine 1? Well, that's what your algorithm has to decide. Maybe it's here.
M1 through Mn is the machine?
Yes, no, sorry. C1 through
Okay.
Cm. Okay. Because I wanted to use the subscript M. So here, I'm going to have the numbers 1 through N in some order. Right? So this job would be fed into machine 1 first, followed by this job, and so on.
Okay.
Now in C2, I have a different order, possibly. Now you might ask, what possible advantage could there be? Well, there is a possible advantage because we're going to add some more factors.
Okay.
Right. So this might be different, something like this. And it's up here. Okay. So each column has the numbers 1 through N in some order. Okay. So that's what we call a schedule. And then you want to compute the penalty for each schedule. So there's going to be a function that assigns a penalty to each schedule. All right, now I think you know what well, I don't know if you do know what an indicator function is. It's kind of like what we were doing before. The indicator function is 1 if you're in the set and 0 otherwise. So,
Okay.
there are other ways to write it. All right, so let's see. Now, when I say objective function, that's the penalty. So there's two. So I should say this. So if I say x is the lateness, and that's 1 or 0. Well, of course, that would be for. Let's do it this way. Let's say for job n, I can say, let's say L of n is equal to the lateness, and that's going to be 0 or 1.
So it's just a Boolean?
Yes.
Okay. Just saying whether
And
it's
then
late or not.
yes, and then T of n is equal to the number of days late.
Okay. So T of n is just the sum of all ln's.
No. If the job is late, there's a penalty, and if the job is, and then you look both at whether the job is late and how many days late it is.
Okay.
I really should do something like this. It's going to look like if I call this time, and this is the penalty, then it's going to be 0, jump, like that.
Okay. Oh, I see. So as soon as we have a late day,
Yes.
that's a trigger. It
Yes.
switches from 0 to 1.
Yes.
And then T is the amount of time that it's late after that.
Yes.
Okay. I see.
So the penalty is going to be, according to this, the penalty is going to be, I think it's called, it's going to be alpha LN plus 1 minus alpha times T of n. So the bigger alpha is, the more the lateness counts.
Mm-hmm.
The smaller alpha is, the more the tardiness counts. So that's how you that's the penalty. That's what we're trying to minimize.
Okay.
All right. Now we have to specify indices. All right. So the job index goes from 1 to n. The machine index goes from 1 to m. And the position index also goes. Well, I think this is wrong. I think this should be 1 to n. I think that's wrong because it's the position on the machine.
Right. And
So-
so it should be the number of jobs. Yes.
Yes. So I'm going to change that. Oh, yes, it's back here. Okay. All right. So then we also have the. Is it here? That's not it. Let me close this because we're getting out of the bird business. All right. So yes. Now, as I said, the time that the job arrives is AI. The time that the job is due is DI.
Okay.
And Xij is the processing time of job I on machine J. And these can be random variables, but we're not going to worry about randomness for right now. And then there's the other factor is something called information delay. Once the job finishes on one machine, then you can't necessarily feed it directly into the next machine. There may be some kind of delay. You might need manager approval. You might need some special part. You may need this. You might need that.
The job done. I have to switch machines.
Well, you are switching machines, or you might have to configure the machine or something. I don't know.
Okay.
But it wouldn't be that because the delay, once the job finishes on machine I, then Zij is the time. So once the job finishes on machine I. Okay. So let's do job I. I really don't like his choice of indices, but let's say it goes into machine J. And the amount of time it spends in here is Xij. All right, then when it's finished, so the job must wait at least Zij before going to the next machine. So you see that if some job has a long waiting time, oh, I forgot to record. Did I start recording?
I think you did.
Oh, I did. Okay, yes. Okay, yeah. Okay, yeah. All right. So if some job has a long waiting time, it might be worthwhile to stick in another job while you're waiting for the first job. into the next. All right. So let's say let's just do a case where we have two machines. Let's do our matrix X and our matrix Z. Okay. So we'll just have two machines, two jobs. Okay. And so this is going to be sorry. So this will be the job index, and this will be the machine index.
Okay.
So this is processing time. So maybe job, I don't know how much this takes, 10 time units here, this takes 20 time units here, this takes 5 time units here, this takes 15 time units here. And then Z, same configuration. Now, actually, this is the waiting, I think the way we have it is the waiting time before. Time interval after which the information will be available. Yes, okay, that's right. So this is the waiting time before. So let's say this is 12, and then this is, I don't know, 2, and then this might be 30, and this is going to be 0. Okay. And then we have arrival times and due times. So the arrival time, maybe they both come at time 0. So sorry, this would be job 1 and 2. So maybe they both come at time 0. And the due time, I don't know, maybe this is due at 50, and then this is due at 32, something like that. I don't know. All right, so you have a choice. So, and I said the schedule matrix, but let's just do a schedule matrix. Let's suppose our schedule matrix is, so I have 1, 2, 1, and then this 1, 2. Suppose in this one I put 1 first and then 2 first, and then this one I put 2 first and then 1 first. So that's J1, J2, and this C1, C2. All right, so what happens? They both arrive, so we'll do a timeline. So let's do the timeline for job 1 and the timeline for job 2. All right, now they both arrive at time 0. Okay. Now job 1 goes to machine 1 first. And it stays there for 10 time units.
Okay.
So here it's in machine 1 until time 10. And job 2 is idle. All right. Now, I'm sorry. I forgot. Mistake. There's a waiting time. Job 1 has to wait at least 12 time units before it starts. And job 2 only needs to wait 2 time units before it starts. So job 1 has to wait 12 time units before it starts. And this goes up to 12. And job 2 has to wait only 2 time units. Okay? Now, according to this, I have scheduled job 1 first. So I can't feed job 2 in. I've scheduled job 1 first, and it's going to take 10 time units. Okay? So here's job 1 is on machine 1 for 10 time units. And that's going to take us up to 22. Okay. Now, according to the Z, job 1 has to wait 30 time units to finish on before it can do the second job. So this is going to be wait for 30 time units. And that takes us up to... Is this kind of making sense?
Yeah.
So how about job 2? Job 2 had to wait this long. Now, because job 1 was scheduled first, we can't schedule job 2 while job 1 is running. Right? Once we do schedule job 2, it takes 20 time units. Okay? So that means here I can start job 2 here, and for 20 time units. So this is going to be machine 1. Okay. And that will take us out to where? It's going to be 12 plus 20, 42. Okay. At this point, job 2 has a waiting time. Now, what's the waiting time for job 2? It's 0. Now, let's just make it 5, just so that it looks like something. And so then this one will have to wait 5. So that will take us up to 47. Okay. And then job 2 gets finished. Job 2 takes, on machine 2, takes 15. So this is 15. This is machine 2. And that takes us up to 47 plus 15, which is 62, right? So job 2 is finished here. Okay. Job 1, in the meantime, has to wait for job 2 to finish here. So job 1, so this is idle. I can call that idle. This is idle here also. This is idle up to this point. At this point, job 1 can kick in, and job 1 takes 5 on this machine. This is machine 2. Okay, and then that will finish at 64 or 67. Finish. Okay. Well, so this.
Why can machine 1 with job 1 and job 2 start at the same time?
Whoops! I made a mistake. That's why. This. I'm sorry. That's wrong. The idle should go to the end here. So that's wrong. Good catch.
Okay, thank you.
This has to wait until the end here. So it's idle all the way up to here. And then how much time did it take on machine 1? It takes 20 time units on machine 1. All right, so I messed up my. Well, let's make it have a smaller time so let's see. So this would this time is 22. Let's just say the time is 10 instead of 20. Okay. So that means this would be on machine 1.
So no jobs or machines can operate at the same time?
Yeah, a machine is occupied with one job at a time.
So you can't have machine 1 and machine 2 operating at the
Oh
same
no,
time?
yes you can.
But because of the order we're going in, machine 1 has to operate before machine 2, so it's occupied.
That's what turns out to happen. I mean, this is a very bad schedule.
Okay.
You would certainly want to. Machine 1 and machine 2 can certainly operate at the same time.
Okay.
It doesn't turn out that way. I mean, if we switch the order around, we probably could make that happen.
Okay.
And you can play around with it, but you see how it's calculated.
Yes, I'm putting it together.
There's a waiting time before you can go on the machine. Then there's your time on the machine. And the other restriction is that two jobs can't be on the same machine at the same time.
And machines have a cooldown. Is that right?
Well,
There's a waiting
no, we
time
don't have a
after.
cool time. It's a waiting time before and not a waiting time after.
Oh, okay.
Well, no, it's a waiting time before and not a waiting time after. The idea is that once the job is finished on one machine, there might be some bureaucratic something, or the product might have a cooldown.
Okay.
That's something that could be. The product might have a cooldown. Right, you heat up some metal and then it has to cool down before you put it in the next machine. That's a possibility.
But that would be added into the waiting time before starting the next machine.
Yes, that's right. That would be a part of the waiting time. That's the waiting time for the next machine, right?
Yes.
But it's a fixed interval. You'd have to wait the same amount whether or not the other machine is occupied. So the waiting depends on the job and not on the machine. Well, it does depend on the machine. But all right. So let's go back here. All right. So you want to minimize. So all right. So okay. So the variables here, they make a lot of sense. In terms of the variables that I showed you, the x's and the z's and stuff, you can certainly define the starting time of job I on machine J. And this Wij(k) is another way to represent that matrix. But this is a Boolean. So Wij(k) is 1 if job I is at position K on machine J. So, for instance, I could, if I wanted to translate this here we would say job 1 is at position 1 on machine 1. So you'd have W111 equals 1. Job 2 is at position 2 on machine 1. So I think that's I forget which one the last index is. Oh yeah, that's job 221 equals 1. And then job 1 on machine 2 is at position 2. Job 2 at machine 2 is at position 1. And the others are 0.
Okay.
All right, so it's a Boolean representation of the same information. I actually don't remember if we do it this way in the I don't remember if this is how we actually implement it. But let's go through. All right. So what you got here is so GK of WS is so what this is doing here, and this is definitely wrong because there's a K here and there's an M here that's not resolved. Oh no, I see. M is the last machine. M is the index of the last machine. This is actually going to give you the lateness. Because what this is saying is, and it's not right, because, no, it is right. It is right. So, what is the lateness of job, shoot, how do we do this? I forget what the last parameter is again. Okay. So, all right, what this is, GK is going to be the lateness of the kth job scheduled. So here, let me do this. Let me grab it and see if you can, because you have to get accustomed to these variables. But you will. You got accustomed to the birds, so. So what does this mean? So GK of GK is going to be sorry, and that's way too small. I don't know why it's so small. GK is the lateness of the kth job scheduled on the last machine, M. Now, why is that? Because what this W is doing is it's picking out from all the jobs, it's picking out which job is scheduled last. So this Wijk, I'm sorry, I didn't say that quite right. IMK, sorry. This picks out which job index corresponds to the kth job scheduled on machine M. All right, so get the distinction here between job index and job order. Job index means the job, you could put a number on it.
Job 1, job 2,
yes,
job
that's
3.
right. I mean, job 1 is red, job 2 is green, job 3 is blue. That's fixed throughout the whole process.
Yeah.
But on each different machine, that fixed job may assume different indices because it's different orders. Mm-hmm. All right. So what WIMK does is it picks out the job index with, the job index is I can call it the job identifier. Right? That identifies
or just the job number?
Or job, you can say job number, yes. Well, but that's also confusing if you're saying job number on a particular machine. This job number is fixed. It's determined for the job.
Yes.
Okay. And that identifies the job uniquely. Okay. So all right. So that's going to pick out the kth job schedule. Then here you have the starting time for that job on machine M and the execution time on that machine. That's going to be the time when it finishes.
Okay.
Right? So SIM plus XIM is the time when that job finishes. And then DI is the due time.
Okay.
Right? So you see what's going on here. That's the time the job finishes, and then you subtract that from the due time. If it's positive, you're bad. If it's negative, you're good. Okay, so positive, bad, and then negative, so less than or equal to 0. I'll just say less than or equal to 0. That's good. And equals is just don't worry about the case of equals. All right. So all right. So what this is saying is that if you look at this is like what I told you, that the alpha. So this one here, this 1R plus means this function is 1 if this guy is positive and 0 otherwise. Okay. So let me grab that so you can see that. So this one here says, this is 1 if and only if the GK of WS is positive. Okay, so that means there's no penalty if GK is less than or equal to 0, right? And what's the penalty? The penalty is alpha, that's the fixed penalty, plus 1 minus alpha times this late amount. We like call it tardiness.
Okay.
Right? So you see how it works. Now you might wonder why I don't have an alpha and a beta, but it really doesn't matter because that would just rescale the whole thing. This is just showing the relative importance of the two. This clearly shows the relative importance of the two factors.
Yeah.
And if I had an alpha and a beta, well, I would just divide them both by alpha plus beta, and you'd get the same thing.
Okay.
So that's what we have here. All right. So that's pretty much the mathematical specific. And then here's a mathematical way of describing the constraints. So if you think about these, they all make sense. Let me copy these, and then I think that's a lot. That's a lot to digest. Once we get through this, we can stop. And you're not taking the linear programming course, but this is an example of linear programming. I mean, it's a linear programming type problem. So the reason why we're not using linear programming is it's too big, and it would break the computer. It gets very, very complicated very, very quickly. I mean, if you have 3 indices. All right, so what does this first one say? Right.
Is that saying that it's late at all?
What this says is that, remember that this means that, well, no, W is telling me, remember, Wij means that job I, it has position K on machine J. Right. So what this is saying is that what this says is that job I has some position on every machine.
Okay.
Right. So has some position on J. The job I has all jobs have to be scheduled on all machines. All right. Now what is this one saying? This one is saying that job I, so here we're summing over jobs. Oh, so each position has exactly one job. That's what this is saying. So each job has a position on each machine, then each position has a job.
Okay.
Okay, on machine J. Okay. Now what is this saying? This is the start time. All right. So this is the start time on machine 1 of job I. Or hang on a second, because because this is I equals 1 to n. All right. So this is machine 1. And this is the first start time. So this is the starting time of the first job on the first machine. Right? Because this is the machine and this is the first job scheduled. W will pick out the first job scheduled on the first machine. Okay. So start, first job, first machine. Okay. And it's going to be bigger than or equal to, and here it's again it's picking out the first job on the first machine. The delay, this is the delay before starting on machine 1, plus the arrival time of job I. Okay. So this must be greater than or equal to the delay. I should put arrival time plus delay, but the arrival time plus delay, but it's the same thing. In other words, the first job, it has to arrive first and wait before it can start.
Uh-huh.
All right. Now what about this one? This one is looking at the K+1 machine. So this one is saying that the first job, no. This is saying that this is the position. This is saying the K+1th job scheduled on the first machine. The starting time of the K+1th job on the first machine has to be bigger than or equal to the this is the finishing time of the kth job on the first machine. Okay, so it says the starting time of K+1's job on machine 1 must be greater than or equal to the finish of the kth job on machine 1. Now what about this one? This one is saying that the starting time of the K+1th job on machine 1 must be bigger than or equal to the arrival time of that job plus the waiting time. So this starting time of K+1's job on machine 1 must be greater than or equal to arrival plus wait. And these are all constraints for machine 1. Those are all the constraints for machine 1. Now, naturally, there's going to be constraints for machines for the other machines. But they closely resemble. And the reason why you separate off the first machine is that the other machines don't have an arrival time, so that doesn't appear.
Uh-huh.
But these are similar conditions. I could go through these. This one is the start time of the first machine. This is the start time of the first job scheduled on machine J. And that has to be bigger than or equal to the completion time on the previous machine plus the waiting time.
Okay.
This one says the start time of the K+1th job scheduled on machine J must be bigger than or equal to this is the same thing. This is the same thing. That job cannot start before it completes and waits from the previous machine. But also the K+1th job on the jth machine has to wait for the kth job on the jth machine. Right? This is the finish time for the kth job on the jth machine. Right? Because that's when it starts and that's when it finishes. So the next job scheduled on that machine cannot start until this is finished. So that's actually a comprehensive specification of the conditions. Because if you've got a job scheduled on a machine, you can't start it until it finished on the previous job, on the previous machine. And you also can't start it until the previous job on the same machine finishes. And that's what this is saying. So it's very, the notation is unavoidable. Oh, okay. All right, so he has the interpretations right here.
Nice.
Okay. Yeah, Richard was a very good student. Richard is like you.
I try.
Okay. Maybe you two guys will meet someday. And his English is actually quite good. All right, so that's the system. So the question is, so now you have the problem. The problem is find a schedule that minimizes this penalty for overall machines.
Okay.
That is the issue. Now I'll have to make sure I dig up the. That shouldn't be too hard.
The code.
The code, yeah, because I've been working with somebody. I'm working with a student from Nigeria, but she is not a programmer. Yeah, it's here. Let's see. I guess it's here. I can share this whole folder with you. It's this one, Flowshop Problem Rev 3. And I can probably... you can see that the main program is here.
Okay.
Well, actually, I'm not sure because there's a V1. Oh, no, this is a V1, but this is older. So I think it is this one. It is this one here. So let's see. So a bunch of packages, a bunch of functions that were defined, and then this sets up a test sequence.
Okay.
We want to generate a random situation and then apply the algorithm. So this just sets up a random situation. And then you see we define all these. We have to define all of these. So this is create an instance. Let's see. Well, actually, here's you get A, D, X, and Z. So you don't really need to worry about this.
Does this just generate a schedule?
Yeah. No, this generates a instance. Means it generates arrival times, waiting times, and execution times and due times.
Oh, okay.
It does not generate a schedule, but it generates the problem, not the solution.
I see.
Now this one, stock fun, this has the problem here, and this will attempt to find the solution. So you can follow this. I think it's probably in this. It's probably in this one here. You can look for it.
Yeah.
All right, here it is. Right. So the current idea behind this is, you can follow here. It says step 1, step 2, step 3. So first of all, you generate some random solution. This is glorified. This is called Monte Carlo, which you may have heard of, which is just glorified trial and error. But it's intelligent trial and error. So you generate an initial solution, and then what you do is you keep a collection. I don't know. You want to say harem or something. You keep a harem of candidate solutions.
Okay.
And at each iteration, you modify one of those. And if it's better, you keep the modification. And if it's don't, you throw out the modification.
Okay.
But you modify it in a way that's it's not purely random. You modify it in such a way that it should you trying to stack the odds so that it's going to be better. Yeah, so here this is the part, generate new solutions one by one. So you record, and what happens is you give each solution a certain number of chances, and when it gets too old, you remove it. Unfortunately, the harem metaphor is very appropriate because that's pretty much what happens? You have you have this collection of jobs. You try them, and then when the job gets too old, you remove it. And then you always record the best solution. So you keep a record of the best solution. So you just keep on running this process, and hopefully find better and better solutions. And then after a while, you don't get anything better, you just stop.
Yeah.
So that's the basic idea. So why don't I, in this document, I will give you the path. So I will share this. Scheduling with uncertain information folder with you.
Okay.
And I will. I can put the path. Let's just select all. Did it select all? Let's try again. Let me make it smaller. Where's my view? You'll really learn something, and this will be a nice challenge, I think, for you. Let me move it down a little bit. Okay. Then this is. Well, now I can zoom back out again. Okay. Well, oh, sorry, I screwed up. Did I paste it again? No, there's just one copy. That's fine. Okay, so it was here. That's not what I wanted. And I really should clean up that folder. And you can execute. You may need to install some packages. I don't know, but I think it's all base. I think it's all base Python. No, actually, there is something that you do need to install, but you'll run across it. There's a linear programming something that you need to install.
Yeah, that's fine.
But you.
It'll tell me if there's anything wrong when I run it.
Do you know how to create environments?
No.
All right, it's something. My South African colleague taught me this. Really, for different projects, you should have different environments because you don't want to mess up your base environment. You want to keep that sort of pristine, and then if you make extra installs and stuff, because sometimes when you install something, you can't install something else because there are conflicts. So let me show you how this works. All right, so it's called Flowshot Problem Main Stochastic. So this is, so let me just copy this, and I'll put that here. Okay. All right. So the way you do environments is, you go to the Anaconda prompt. Well, what you do, I tell you what you do. You Google it. You go to Anaconda. Yeah. You go to Anaconda Create Environment. But let me show. I'll talk you through the steps. And it takes up some storage on your computer. So, but it really does. It can prevent problems. Oh, don't do it in the console. That's it's better to do it in the Anaconda prompt. Let's see. Well, let's see. Yeah, yes, you do. You use this conda command. Yes, okay. So yes, yeah. So you just do this. conda create dash dash name, and then your new environment name. And then, yeah, this is very straightforward. Oh, I see. Now, what you should do is clone your base environment. So let me just say that here. You should create a new environment, clone your base environment, and then use that. So let me see. I'll look that. Let me see. Okay. I can probably just do this right now. Right. Now the problem is that I can't get out of the base environment. I can't get out of the base environment to clone.
I'm not sure if it'll be that much of an issue.
You can do something. You can.
I think this could be a bridge that we cross if we get there.
Well, I mean, you will get there because, I mean, if you don't mind, I don't know how much you use Anaconda.
For research, exclusively.
Well, yeah, okay. This will probably not mess up because in the bird project we don't use any special packages. So it's probably okay. Well, all right, yeah, maybe you can just say that. We'll cross it when we come to it. But I actually want to do it myself because I need to make sure I don't mess up my environment. So let me figure out how to do it, and if I find a good reference, I'll send it to you.
All right, that works.
All right, good. Well, let me stop the recording. You've been on for quite a while here. You've been very patient. Hopefully the audio